Good afternoon or good evening. Regardless of your time zone, I'm glad you're here. My name is Axel Gonzalez, and I'm excited to present the research project I've been working on for the past semester. This project is titled Robust Interpretability with Self-Explaining Deep Learning Models for Computer-Assisted Classification of Kidney Stones in Endoscopic Images. Before diving right into details, I'd like to introduce my mentors, Dr. Gilberto Ochoa Ruiz and his PhD student, Daniel Flores Araiza. They both are from Tecnológico de Monterrey Campus Guadalajara. And as for me, I'm a bachelor's student in robotics engineering at the University of Guadalajara. Computer vision, neural network design, machine learning, and deep learning are some of the pillars of my degree. And this sparked my interest in the vast field of AI. This interest led me to apply for the LXAI Google CSR program, where I was fortunate enough to be matched with this marvelous project and these wonderful people. Now, I'll gradually take you to discover what we're doing by combining AI and medical imaging. Artificial intelligence has become an integral part of our daily lives, revolutionizing various fields with its ability to analyze vast amounts of data. With the release of ChatGPT and other intelligent chatbots, everyone's attention has turned to AI. In medicine, the combination of AI and advanced machine learning techniques offers unprecedented opportunities to enhance diagnostic accuracy, improve patient outcomes, and streamline healthcare processes. AI-driven technologies are particularly transformative in medical imaging, where they assist in the rapid and precise identification of diseases. For instance, AI algorithms can classify medical images with exceptional accuracy, often surpassing human capabilities. This is crucial in areas such as radiology and pathology, where rapid diagnosis can significantly impact treatment decisions. But the lack of interpretability in these models presents a significant challenge. In clinical settings, it's not enough for a model to be accurate. Healthcare professionals must also understand the reasoning behind its predictions to trust and effectively use it. Our project then exemplifies the synergy between AI and medicine. By leveraging self-explaining models, we aim to develop an interpretable and robust system for classifying kidney stones in ex vivo datasets. This not only enhances diagnostic accuracy, but also provides valuable insights for clinicians, fostering trust and facilitating informed decision-making. There are various methodologies in which a computer can identify an object in a picture. But how does our model do it? The answer is part prototypes. They refer to distinctive parts or features of an object that can be used to help identify and classify the whole object. These part prototypes act as building blocks or templates that a computer algorithm can match within an image to recognize the complete object. For example, we're trying to recognize a car. Part prototypes might include the shape of a wheel, the contour of a window, or the outline of a headlight. By identifying and combining these part prototypes, the algorithm can accurately classify the image as a car. But not everything is always nice and neat. The model can fail. For instance, what if the model misinterprets the front of a car as an old-fashioned radio, like the ones our grandparents used to listen to music or the news? Failing is quite common in computer vision, but we can take advantage of these mistakes. By understanding why and where the model fails, we can adjust our network parameters and retrain the model, enabling it to correctly identify the objects it previously confused. But how can we know the why and the where? Well, eXplainable-AI, or XAI for short, it is said to be tools and frameworks that help to understand predictions made by our model. On this field, providing evidence for the output of a model is of extreme interest, since a better understanding of how the model works could be gained. But furthermore, to evaluate whether the output deserves credibility or not. These are the foundations of our research. Over the last 6 months, my primary task has been modifying a dataset of over 2,400 kidney stone images. This involved using the image corruption Python package from the GitHub repository carrying the same name to apply various alterations to the images. In total, 19 different corruptions were applied. Most of them were based on adding noise strategically, such as Gaussian noise or pixelate. And I applied a special set of 4 corruptions as part of data augmentation. These were speckle noise, Gaussian blur, spatter, and saturate. According to the image corruption repo community, these are the corruptions that will truly test our model's robustness. Each corruption was applied at 5 levels of severity, with higher levels indicating greater noise. Images at level 5 exhibit more pronounced effects, in the given example an increase of brightness and pixelation compared to those at lower levels. If we take into account that 5 models were used, times 5 severity levels, times 19 different corruptions, this means that 475 evaluations were made. The metrics obtained from evaluating the model's classification accuracy reveal how these corruptions impact its performance. Accuracy tells you overall how many predictions were correct, how many of the predicted positive results were correct. Recall tells you how many of the actual positive results were correctly identified, and F1 score gives you a single metric that balances precision and recall. Since these metrics are expressed as percentages, we can gauge our model's performance by how close the values are to 1. What truly matters, higher values indicate better performance. As the values approach 0, the model's classification ability deteriorates. A model performs better without perturbations compared to the same model tested with perturbed data. We can observe this by comparing the metrics obtained from testing the model with the original dataset and the metrics from testing it with corrupted datasets. Speckle noise at severity levels 3 and 5 in this case. Focus on the results and see how they decrease insignificantly as we apply corruptions. The reason for applying corruptions is to simulate real-world conditions where our model might encounter poor resolution images. Identifying where the model fails is beneficial for research as it allows us to fine-tune and adjust the model's parameters to achieve higher accuracy. As part of my work in my mentor's council, I learned how to use MovaXterm to seamlessly connect a physical location with a virtual environment, enabling access to external memory. My practice with GitHub was reinforced, particularly in creating and updating repositories, which is essential for version control and collaborative work. I also gained experience in drafting a paper for a conference, academic writing, and the process of preparing research for publication. At the beginning of this project, I was introduced to key concepts. We delved into deep learning theory, focusing on explainability and convolutional neural networks, providing all the foundational knowledge needed to understand the work done previously. I am very happy to have gained this experience early in my academic journey. I had the opportunity to network with fellow researchers, facilitating the exchange of valuable opinions and ideas that contributed to our work. I also agree with my mentor, Daniel, who always reminded me, a new person you know could be a new door opening in the future. I have learned to work smart, not just hard, and to manage my time effectively to ensure progress. Adaptability has helped me control anxiety and avoid the trap of thinking there is only one way to accomplish things. Project methodologies are always subject to change to achieve better results. When I had problems, such as code errors that I couldn't debug, I would discuss them with my mentors. They dedicated time to analyze the situation differently and encouraged me to think outside the box, instead of just pointing out my mistakes. This has helped me develop a problem-solving mentality. As a final thought, accurate and rapid classification can help provide appropriate treatment to patients, which can extend their lives or enhance their quality of life. I'm fully aware of the advantages we can gain by integrating computer vision into a project, and I'm intrigued by all the aspects of life that this tool could boost. I would like to thank all the mentors of the LXCV program for making this a wonderful experience and giving me the opportunity to be a part of it. I look forward to meeting you again in the future and discovering how we have continued advancing research and developing new AI techniques to improve people's lives. I'm leaving you my contact information here. You can reach me via email at axavarog2805@gmail.com or view my LinkedIn profile at the address below. Thank you for your attention.